Good morning everyone. This is Dr. Sarthak Sarkar and I am an assistant professor in the division of applied mathematics IIIT Delhi, and the course that I will be presenting on via the NPTEL channel is on variational calculus with specific applications in control theory and nanomechanics. So, this introductory video I am going to mainly cover the course description, the weekly course content as well as the references that we will be using throughout our course discussion. So, the course description, this course is mainly on the theory and applications of variational calculus. Roughly 80% of the course will be on the development of the theory of calculus of variations, while the other 10% is on specific applications of calculus of variations in optimal control, while the final 10% will be on the second application in nanomechanics, namely the oscillatory motion of carbon nanorods. We are going to, throughout our lecture discussions, we are going to introduce problems specially related to geometry, differential equation and Newtonian mechanics. I will assume that a basic background of multivariate or vector calculus or differential equations and high school or class 12th basic physics mechanics is there for the students who take this course, and this course will be mainly serving as a reference study and research introductory research course for final year undergraduates and first year PhD students, especially those who are working in the area of industrial control systems, instrumentation engineering, nanoscience as well as the analysis component of software development. And as mentioned earlier, throughout this course I will be doing solved examples not only related to maths, but also physics and towards the later half problems in chemistry and biology. So, the weekly content, the first week of the course will be mainly the introduction to calculus of variations, namely the history of the calculus of variations and the various applications. We will be introducing the statement of the problems with several on the several topics, including the gold diggers problem, the catenary, brachistochrone, the DDoS problem, the geodesic or the shortest path problem with its extension to minimal surface problem and the problem of optimal harvest in economics. We are going to do some revision in finite dimensional calculus, where the concepts will be later on useful to develop the theory in functional calculus, namely the development of Euler-Lagrange equation. In the second week we will be doing special cases of solution to the Euler-Lagrange equations, the special 4 cases, and then we will be generalizing the solution to Euler-Lagrange for functions or integrands containing higher derivatives, also known as the Euler-Poisson equations. In the third week I will be continuing the generalization of Euler-Lagrange equations for functions containing several dependent variables or for functions containing more than one independent variables. I will be also touching upon the numerical solution to Euler-Lagrange equation for problems where the analytical solutions are not possible. In the fourth week I will be looking at the constraint optimization problem. I will start with again the revision in the finite dimensional case or the case of Rn, where we touch upon the topic of Lagrange multipliers with single constraint as well as multiple constraints, and also those problems which cannot be directly solvable with Lagrange multiplier or the abnormal problems. We will then focus our attention to the functional optimization, the constraint functional optimization, including the generalization to integrands or functions with higher order derivatives with multiple isoperimetric constraints as well as several dependent variables. In my fifth week I will look at another 2 sets of constraint optimization problem, including those involving holonomic or algebraic constraints or non-holonomic or differential constraints. I will also start discussing the problems with variable endpoints leading to the formation of the natural boundary condition, and also look upon an example in this class of problems, namely the problem of elastica. In the sixth week we will continue our discussion for problems with variable endpoints, including the discussion of the transversality condition as well as the corner conditions for broken extremal, famously known as the Weierstrass-Erdmann condition. We will also look at an example an example for broken extremal problems, namely related to the design of aerodynamic surfaces, and then towards the end of this week I will touch upon another formulation of Euler-Lagrange, namely the Hamiltonian formulation. In the 7th week I will continue my discussion on the Hamiltonian formulation, including the generalization to several dependent variables. I will also introduce the concept of symplectic maps, which converts one Hamiltonian system into another Hamiltonian systems, that is from one coordinate to another. I will then focus upon discussing how to find these symplectic maps via the so called generating functions, which are derived from the solution to the Hamilton-Jacobi equation. I will also look upon the ways, specifically as a particular way to solve the Hamilton-Jacobi equation, namely the method of separation of variables. In my 8th week we will touch upon the concept of variational symmetries, or the transformation which reduces my Euler-Lagrange equation into simpler form. We will also discuss the Noether's theorem, which relates to the concept of variational symmetry. We will then look at the sufficient condition to determine the nature of the extrema found using the first variation, namely looking at the second variation of the functional. In my 9th week we will continue our discussion on finding the sufficient condition for the functional optimization, including the topics of conjugate points, Jacobi necessary condition, the accessory equation, as well as finding these points. We will then start our discussion on the specific application of calculus of variation, namely in optimal control theory, and then in the next week we will look upon the topics of constraint optimization in control theory, and also including the discussion of the famous Pontryagin minimum principle, and also the Hamilton-Jacobi-Bellman equation, which is the Hamilton-Jacobi equation version in the control theory. We will also look upon the other forms of constraint optimization, other forms of solution of constraint optimization, namely via penalty method or via slack variables. We will then in the next week look at another applications of the variational calculus, namely the application in nanomechanics, or the motion of the oscillatory motion of carbon nanotubes. We will first form the basis of this problem, namely the discussion of certain special functions, including the Pochhammer symbol and hypergeometric function, and also the basic chemistry is also discussed, namely the van der Waals interaction and Lennard-Jones potential. Once all these background is built, we will then describe the motion of double walled carbon nanotube via Hamilton's principle. The last week will be mainly to cover some of the problems that were remaining in the previous 11 weeks, and also discuss some additional problems. So, I am going to finally provide some of the course references that we will be using are mainly these two course references, which will be through which we will be covering about 80 to 90% of the course content, and then the third reference is all about the problems and the exercises through in which we will be some of these problems we will be discussing in our lecturing sessions. There are several other references as shown here by the 5th and the 6th, which are the classic references, and then there are later references as shown by the last one. So, I will end my introductory video here by mentioning that a basic background of and the knowledge of finding the maxima or the minima of functions, or the basic knowledge of multivariate calculus by the students is required. As said in the words of Leonhard Euler, or the famous mathematician who is often credited with being the father of calculus of variations, the world is quite perfect, and in fact created by the wisest creator, and there cannot be any rule in which no maxima or minima occurs.